Okay, so there are some vectors we're going to use quite a lot. So we want to talk about those vectors right now. So let's talk about something called a position vector. By the way, let me just back off. So the last time I taught this class, I told the students to go home and practice adding vectors and practice subtracting vectors. And before the next class. Then the next class rolled around, and I had them do some problems where they had to subtract and add vectors. And I was really disappointed that half of the class was clueless. So they hadn't done the work. And so the class was kind of a waste of time for half of the class anyway. So look, you have to know how to add and subtract vectors. So learn it, and learn it soon. Don't procrastinate. Okay, so there's my little speech. All right, position vectors. So here are two streets that intersect. And you want to make a coordinate system, right? Well, gee, don't you think it would be sort of natural to call the intersection the origin? Yeah, that makes sense. All right, so the origin is chosen to be the corner. And again, it's just a choice. You can put it wherever you want to put it, but it seems logical. Now, this is the start. So there's some person here, Sam, okay? So this is Sam, all right, where he starts, and this is where he ends. Okay, fine. So position vectors. Position vectors are drawn from the origin to the location of the object. So this is the initial position vector. So it's called R0. You don't have to say R0. Some people like R, like with a subscript I, like this. In fact, we'll do this a lot later on, right? R initial, and then maybe like R final or something like that. But it doesn't matter. Just label it whatever you want to label it. Just be logical, Okay, so this is the initial position vector. Starts at the origin, goes to the initial position. Kind of makes sense, right? R0. Okay, now this is the final position. So this is R1 or R final, whatever you want. Right? Again, it starts at the origin, goes to the position. Okay, so let's read it. All right, so yeah, the origin is chosen. Yeah. Okay, so here it is. So after Sam walks 100 feet northeast, his new position is R1. Okay, so basically, look. So Sam, he starts here and he walks here. So start, finish. No kidding, right? Okay, so R initial or R0, R1 or R final. Now, what's Sam really doing? He's going from here to here, right? So this is called the displacement, or the change in position. So see that little triangle? That's not a triangle, it's a delta, right? So it's a delta. It means change. We'll use it all the time in physics, okay? So, this is true. This is an initial position vector. This is final position vector. But what's really going on is he's walking from here to here, right? So his displacement, that means change of position. Displacement, change of position is from here to here, all right? So Sam's displacement, delta R, is the vector drawn from his starting point to his ending point. Pew! Okay? That's really all there is to it, all right? That's all there is to it. Okay, so displacement, which is the same thing as change in position. Change in position. Okay, so here's a question for you. We have 1, 2, 3 vectors. So please write down the vector equation. In other words, what equation relates this vector and that vector and that vector? If you were paying attention and you know how to add vectors, this should be easy. So pause your video and write it down, please. Okay, so this is just vector addition, right? This plus this equals that. Now, let's just write it down. So R0 plus delta R equals R final. Now, what does that mean? I mean, it means you start somewhere, you move, and you end somewhere else. Whoopee, right? Doesn't that sort of make sense? Of course it does, right? Start, move, and end. Okay. All right. Now, generally speaking, what we really care about is the displacement. So let's solve for it. So you subtract that from both sides. So therefore, you get the displacement is equal to r final minus r initial. Okay? So it's again, the displacement is the change. The change in position is the final position minus the initial position. So this delta thing is always going to be final whatever minus initial. All right? It could be the change in velocity, the change in acceleration, the change in who knows what, change in electric charge. It's always going to be something final minus something initial. That's how it's defined. Okay? All right. Now, okay, I already said that. I already said that. Okay, so I said that, right? That plus that equals that. But what we really care about is the displacement. So delta r is r1 minus r0. Okay, so yay! I keep saying the same thing. So delta q, when q is whatever you want, delta q is defined to be q final minus q initial. Okay, great. Now, here's the question. You know, Sam, in the previous slide, walked from here to here, right? Now, so this is the displacement vector, right? His change in position. So does this change in position, does this vector depend on the coordinate system? What do you think? Well, so let's put a different coordinate system, right? So let's use this coordinate system, all right? Just for fun. So this would be the initial position vector. This would be the final position vector, right? And, you know, and so what do you notice? This doesn't change. Of course it doesn't change. I mean, come on. This is a person walking, right, from a position to a position. So this is never going to change. I mean, the origin is going to change depending on where your coordinate system is. So the position vectors will change, right? I mean, look at this, right? So here, you know, that's a position vector, that's a position vector, because the origin is here. Now the origin is here, so you have different position vectors. But the displacement will never change, all right? Because it doesn't depend on coordinate system, because this is, you know, this is what really happens, right? These position vectors are just something that we impose, you know. But what is important, what's physically significant is the displacement, which doesn't matter on the coordinate system. Okay, let's see. All right. So all we've been doing so far is talking about the position of an object. Well, you know, in the real world, most things move, right? And so we need to talk about moving, okay? So you already know this. You should anyway. So what's the average speed? The average speed is the total distance divided by the total time, right? That's all it is. I mean, you know, so it's 16 miles to Haleiwa. And let's say it takes you an hour to get there on a bicycle. So what's your average speed? 16 miles an hour. Now, are you always going 16 miles an hour? No. You know, there's hills, there's stop signs, there's crazy drivers, you know. I mean, you know, but that's what average speed is, right? Total distance over total time. And we're not going to use that very much, so whatever. Matt, now look at that. Is that a vector or scalar? It's a scalar because there's nothing here to indicate direction. So it's a scalar. All right. Okay, now this is average velocity. So that's why, so right, the velocity, you know, vector, average. And it's the displacement divided by the change in time. And we'll use that once in a while, not very often, to tell you the truth. Okay, is this a vector or scalar? I already gave it away. And you know what it is. You see the vector signs, right? It's a vector because it has direction. It has direction. Let me just beat this to death. So here's a speedometer in a car. Must be European or something. Kilometers per hour, right? And is there anything with direction there? No. So speed is a scalar. On the other hand, if you have your speedometer plus a compass, now you know the speed, which is a scalar, in the direction, which is kind of magnitude, right? I mean, direction vector, right? So these together, magnitude and direction, give you a vector, according to the Despicable Me movie, right? All right, so that's velocity. Magnitude and the direction. All right, it's your turn again. So, motion diagrams, we like them. The figure above represents a multiple flash photo of two balls moving to the right, motion diagram, and shows both balls at several numbered times. The time between flashes is 0.2 seconds, and the large divisions on the measuring rod are centimeters. So 0, 1 centimeter, 2 centimeters, 3 centimeters, and so on. So what's the speed of the lower ball? So please pause your video and figure it out. Okay, what's the answer? The answer is 6. Now, there's more than one way to figure this out. Let's just do it one way. Okay, the time between flashes is 0.2 seconds. So this is 0, 0.2, 0.4, 0.6, 0.8, 1 second. Okay? All right, so speed is distance over time. We know that the time is 1 second. Now what's the distance? 0, 1 centimeter, 2, 3, 4, 5, 6. So it's 6 centimeters over 1 second. So we just say that's 6 centimeters per second. Now that's not, that's not the only way to do it. And we could have gone from here to here, Let's do that. So what's the distance? Well, this is a centimeter. So this is 0.2, 0.4, 0.6, 0.8, 1, 1.2. So it's 1.2 centimeters. And what's the time? The time between flashes is 0.2. So 0.2 seconds. So what's 1.2 divided by 0.2? 6. So it's 6 centimeters per second. So you can do it any way you want, But by the way, notice something, right? If it's speed, it's a distance over time, so the units always have to be a distance over the time. So you never want to write this for an answer. 6, because it doesn't mean anything, You have to say 6, for this problem, centimeters per second. And we'll talk more about units as we go, but you'll see that units are your friend, and I'm serious. If you're taking a test and you have the wrong units, you know you're wrong. So units really, really are your friend. So you want to treat them as algebraic quantities, right? The distance is centimeters, numerator. Time is seconds, denominator. Centimeters, numerator. Seconds, denominator. So really, really watch your units. Okay. All right. During the 2016 Summer Olympic Games, Karen Clement from U.S. won the 400-meter hurdles race in 47.73 seconds, which is amazing because you have to, so you have to do one complete lap around the track, okay? One complete lap. So you start and you finish at the same place. One lap around the track. And for the 400-meter hurdles, they have 10 hurdles, and they're like this high. So you have to run one lap, hurdling 10 hurdles this high. It's incredible. 47.73 seconds. Amazing. All right. So again, one lap, okay? So you start here and you end here, okay? All right. So what was his average speed? So pause your videos and figure it out. Okay, average speed is the total distance over the total time. His total distance is 400 meters. His total time is 47.73 seconds. So, that's the average speed, right? Okay. All right, on the other hand, and note there's no direction. Well, I don't care about that. Forget it. Okay, on the other hand, what was his average velocity? So pause your video and figure it out. Okay, so average velocity is the displacement divided by the time. Now look, if you start and end at the same place, what's your displacement? In other words, what's your change in position? 0. So therefore, this is 0 over 47.73 seconds. Well, that's 0, right? 0, okay? So his average velocity is 0. So he got a gold medal, even so his average velocity is 0. Okay? And that's just because he started and ended at the same place. So you really got to be careful when you're talking about speed and velocity, all right? Okay, so let's see, we've talked about position. We've talked about velocity. Well, what if the velocity is changing? I mean, that happens all the time, right? Sure, of course it does. All right, so if the velocity is changing, we have the change in velocity divided by the change in time. Okay? All right, now let's see, how can that change? How can that change? How can the velocity change? So think of a car. How can you change the velocity of a car? Well, most people say the brake, right? Slows it down. Or the accelerator, it speeds it up. Okay, now that's magnitude. How about the direction? The steering wheel, right? So there are 3 ways to change the velocity in a car. The brake, the accelerator, and the steering wheel. Because remember, velocity is speed as well as direction. Okay, so for this chapter, we're just going to talk about increasing and decreasing speed. We'll talk about changing direction in chapter 4. All right, so this is the equation for the average acceleration. All right, it's the change in velocity over the change in time. By the way, these equations for like displacement and average velocity and average acceleration, we're going to use those forever in physics. And so you should just memorize them. I mean, because they're that important. All right, so that's average acceleration. And here's an example of accelerated motion, okay? So free fall, so this is free fall. So free fall is like it says, right? So we just drop something. That's called free fall. Now you got to be careful. Free fall is when we ignore friction or we ignore air resistance. So for example, now that was not the example of free fall, right? Because air resistance is very, very important. But if we're just in, this little room here and we just drop something not very far, well, air resistance is not important, so we just call it free fall, right? So the gravitational force is the only thing that we care about. We don't care about air resistance, okay? So here's an example of free fall, right? It's accelerated motion. It's going faster, 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 faster. So that's a very common example of accelerated motion, which we'll see and describe in gory detail later on. All right, so we've talked about the basics, right? Position, velocity, acceleration. Now we're going to do something that most students consider tough or difficult. We want to recognize the relationship between velocity and acceleration when an object is speeding up, slowing down, or at a turning point. Okay, so let's do it. All right. So here's a question for you. So V average equals the displacement over the time. So the directions of V average and the displacement are what? So think about it. So pause your video and figure it out. Okay, I hope you understand. Okay, well, it's the same. Well, why? Well, because delta t is always positive, right? You can't go back in time. I mean, delta t is t final minus t initial. It's always going to be a positive number because we don't go back in time, okay? And the direction is given by the sign, plus or minus. So this is always positive, so who cares? So it's out of the picture, basically. So if this is positive, then this is positive. If this is negative, then this has to be negative, all right? So the sign of this has to be the sign of this, because this is always positive. So if the signs are the same, it means that the directions are the same. That's how you figure out the directions, by the signs. All we're doing is one-dimensional right now, by the way. Okay? All right. So the directions are the same. Okay? All right. Now, what we want to do is we want to carefully consider this. So A average equals delta V over delta T. All right? We want to carefully consider that because we're going to learn a lot. All right. Oh, there it is. Very nice. All right. Okay. Well, the directions A average and delta V are what? Well, that should be easy, right? So pause your video and figure it out. All right? The same. Why? Same as before. Delta T is always positive. So if that's positive, that's positive. If that's negative, right? Okay, because the signs give you the direction. All right? Okay, so what am I saying? I'm saying if you want to find the direction of A average, that's the same thing as the direction of delta V, right? It's not magnitude because, we're ignoring delta T, right? This is just the direction. All right, now hold it. How do you find the direction of delta V? Well, what is delta V? So this means direction of V final, minus V initial, okay? So in order to find the direction of A average, all you need to do is do the vector subtraction and find the direction of that. That's all. So this is the important thing, all right? This is the thing that we're going to use a lot. The direction of A is the direction of delta V, which is the direction of V final minus V initial, because delta V equals V final minus V initial, right? Okay. Now notice we don't know anything about the magnitudes. All we're doing is the direction, right? Just the direction. That's all we care about. All right. So let's see. We're going to write that somewhere. All right. Okay. All right. Now we're going to have the fun part. Okay. So students have trouble in physics oftentimes because so this is my opinion, because they philosophize. They don't analyze. They just kind of think about things, but they're not really using any proper analysis. They just use their gut rather than their brain. Okay? So what we want to teach you is to use the laws of physics to analyze things properly. Don't just guess or don't just philosophize, all right? So here's a good example of that. All right, so let's see. The average acceleration of an object is positive, all right? So the average acceleration of an object is positive. So what do you know about the speed? The object's speed is what? All right, so pause your video and think about it. The average, all right, so now we're back. So come on, the average acceleration is positive. So what do you want to say? Most people want to say number 1, but guess what the answer is? Number 3. There's not enough information to decide. What? Okay, so what are you talking about? So we got to go through this and see if it's true. So let's do that. But before we do that, again, right up here, the direction of A average equals the direction of delta V. Oops. Delta V equals the direction. All right. So let's actually analyze this, all right? Analyze it. See what in the world's going on. Okay. All right. An object's motion diagram is shown below. Got it. So yeah, sometimes, instead of just drawing the dots, they just label it like this is the initial velocity and this is the final velocity. Okay, that's okay. You don't have to label them like 1, 2, 3 or something like that. Okay, so an object's motion diagram is shown below. Great. What is the direction? What's the sign, which means the direction of A average? Now, don't philosophize. We know that the direction of A average is the direction of delta V, which is the direction of V final minus V initial. So there's no philosophizing. You just do it. Do the vector subtraction. All right? So everybody pause your video and do the vector subtraction. Okay, we're back. All right, so V final minus V initial equals V final plus negative V initial, right? Okay, that's cool. So V final is this. That's V final. And then minus V initial is that way. Agree? It's that way. Okay, I don't want to draw it on top of this because it will be messy, right? You won't be able to see anything. So I'm going to draw it, I'm going to just draw it a little bit above, right? So head to tail, right? There's V final. We want to add minus V initial. So it's going to be something like that, right? So that's minus V initial. So head to tail, right? That's our head to tail. So we go from the beginning point to the ending point. So there it is. So that's our delta V. Okay? So what is it? Delta, so the direction is what? It's positive. Agree? It's positive. That direction. Remember? That's positive. That's negative. Remember we decided that? Okay. So you find this out by doing the vector subtraction, not philosophizing. Okay, now, what's true about the object's speed? Well, I mean, you can pause your video and figure it out. It's sort of obvious, right? Here, remember, this is a motion diagram, so this time is the same as that time. So here it's going, fast. Here it's going what? Slowly. So what's happening to the object's speed? It's decreasing, right? It's decreasing. Okay, so what did we just figure out? So we just had a situation where A average was positive. A average is positive and decreasing speed. All right, now that might seem a little strange, right? We had positive acceleration, but decreasing speed. Well, come on, that's true. Okay, all right, that's cool. Okay, now let's do another one. All right, so do the same thing, right? Find the direction of A average. So pause your video and do it, please. Okay, you're back. All right, let's do it. So V final is this way. And then minus V initial is this way. So again, I'm not going to draw it on top. I'm just going to draw it a little bit below, right? So minus V initial is this way, right? And we go from the beginning to the end. So what is it? So it's this, right? So that's delta V final. I mean, that's delta V, right? Right? From the beginning to the end point. Okay, so what's that? That looks pretty positive to me, right? Delta V is positive. Now, what's true about the object's speed? Well, come on, it's obvious, right? So slow, fast. So the speed is increasing. Okay, so here's an example where, again, we had A average is positive and increasing speed. So, look, A average is positive, decreasing speed. A average is positive, increasing speed. So, if you only know the sign of A average, what do you know? Nothing. All right? You don't know if it's increasing speed or decreasing speed. You don't know. It's as simple as that. So I didn't lie when we went over that, right? The average acceleration is positive. What do you know? Nothing, right? You don't know. You don't have enough information. Okay, so ta-da, right? Got it? All right. Okay, so we got to figure this out. Next video. Let's quit.